Hello folks, today in this video we're going to be talking about electrostatics, part 3, where we're going to take a look at electrical potential energy and electric potential and contrast those with some variables we've seen before, like forces and fields. Let's go ahead and get started. So what is electrical potential energy? Well, we give it the symbol U with a subscript E, and it's just like many other potential energies that we've seen before in this course. For example, everyone knows gravitational potential energy. That's where you take some object like a ball, and you know that if you lift it off of the ground, it's going to gain gravitational potential energy. Why? Well, because you applied a force to it and you had to lift it and do work on it to get it from the bottom to the top. And doing a force over a distance is work, and work increases energy. So you know it has gravitational potential energy. Well, the same thing works for electrical charges. If you had a positive charge sitting next to a negatively charged sphere, it would also take work to remove that charge and get it away from that negatively charged sphere. You would have to apply a force to it over that distance. That would do work, and that would increase its energy. So electrical potential energy is the energy stored in like the arrangement or configuration of charges. Now, what do we mean by configuration? We mean how they are oriented in space. What are their distances from one another, and how are they put there? And this makes sense. It's a very similar type of energy, and you can imagine it works the same way as gravity too. If you were to then release that positive charge and let it go, it would then be attracted to the negatively charged sphere, and then it would go backwards and then fall back down and gain kinetic energy and lose that potential energy. So some principles we have for electrical potential energy is that charges flow from high to low potential. We know that. And then we also know that the amount of energy stored is equal to the work done in creating the configuration. Now, what we mean by creating the configuration is a very specific thing. The idea being that the electrical potential energy is zero if the charges are infinitely far away from each other. If they are very far away, it is zero. And so then it's by creating the configuration, we mean bring charges together from infinitely far away. That's what we mean by bringing them together from a zero potential energy perspective there. Okay, let's take a look then at this a little bit more mathematically. So mathematically, we can define electrical potential energy using the function for work. We know that the work done on a system, is equal to force times distance. And so I can replace this term for work here, because work is equal to the change in potential energy, with force times distance. Now, I wrote this delta R in a very specific way. It's the change in distance between the centers of the charges. What that means is that you can't just pick any distance to move these objects in between. If you were to move them in such a way that the center of them don't get any further away, there will be no change in potential energy. It has to be a distance that is physically getting them further away from each other in terms of their centers. Once you have that, you can calculate your change of potential energy. Now, this also helps us kind of develop an equation for the absolute potential energy of a system. Absolute meaning like, it is the potential energy. You can see that we're taking a force and multiplying it by distance. And you might recall that the electrical force equation is K Q1 Q2 over R squared. Well, if I take both sides and multiply by this distance, this R will cancel out one of these R's, and I am left with this equation right here. So that's where that equation comes from. Just saying that potential energy is equal to K, the Coulomb constant, times Q1 times Q2, divided by just one R, not R squared. So unfortunately, they're very, very similar equations. And you would use this equation anytime you're trying to figure out the potential energy of a group of charges. So if you have a bunch of particles together and you want to find their potential energy, you would use that one. This other equation is more useful when you're thinking about electrical fields, where you're not thinking about like individual charges, but maybe there's a whole bunch of charges that you would want to explore. So this tells you that the change in potential energy is proportional to QE, or equal to QE d cosine theta. What am I meaning there? Well, Q and E, that's coming from this electrical force term up here. Remember that force is equal to Q times E, where E is the electric field strength. So that's just telling me in writing this, not in terms of forces, but in terms of electrical fields. You'll see down here, I've got a picture of a high potential, low potential energy system setup. And essentially the idea is that if you have a bunch of positive charges here, there's an electrical field pointing downward toward those negative charges. And so this equation would help me if I wanted to think about how much potential energy difference there is for a charge moving between the high potential and the low potential in this field. D then is the distance that you move in the field. And then this angle here is very important. Just like I said, the change in distance above had to be between the centers of the charges. This angle takes into account the fact that the movement must be parallel to the field. And this is something we don't think about often because it works really easily for gravity. But if you take a box and you have it lifted up and you move it horizontally forward, you haven't changed its gravitational potential energy at all because it's still at the same height above the floor. Mathematically, you can think about that like the distance that you moved the box was at an angle, a 90-degree angle, with the force that is pulling down at the box. This equation works the same way, where if I take some particle, let's say it's this test charge here, this positive one, and I move it to the right in this field, that would take no work. There'd be no change in potential energy because I'm not getting it any closer to the positive charges. So there's no like repulsion, but I'm not getting it closer to the negative charges. So there's no attraction either. There'd be no change in that potential energy. The only way to get a change would be to move it such that there's a component of that distance in between the electrical field, this is E here, that arrow, and where I'm moving it. And so that angle, theta, is between the electrical field vector and the distance. So we'll put that formally here. That is the angle between the electrical field vector and the displacement vector. And when I say parallel down here, movement must be parallel to the field, that's capturing the idea that this is a cosine. Because if you want to make the cosine a maximum, you would plug in an angle of 0. So if you are parallel with it, if you're moving down one of these lines, your angle is 0. And so you're going to get the maximum amount of work. Whereas if it's at a 90-degree angle, we've already said a 90-degree angle would then go ahead and give you a cosine of 0, and you would get no change in potential energy. Let's go ahead and try a couple of examples here then. So we've got here 2 charges, and I'll move my video down here so it's a little easier to see. Don't want to go back. 2 charges, though, are in this configuration, Q1 and Q2, both plus 5 coulombs, and they're separated by a distance of 8 meters. Asks how much work was done in constructing this arrangement of charges. Well, in order to figure that out, I would need to figure out which equation that I want to use from the previous screen. And I had mentioned that you would use this second equation more often when you have individual charges and you want to figure out the potential energy. This one you're going to save and use if you're moving something within a field. And then this top one is mostly just a definitional thing. So you won't really be using that much on its own. So we got 2 charges here. They're plus 5 and plus 5. And I know that my equation, U of E, is K Q1 Q2 over R. So plugging in my numbers, K is the good old Coulomb constant, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. That's multiplied by Q1, 5 coulombs, Q2, 5 coulombs, and divided by the distance, 8. And here I do not have to square it because it is potential energy and not force. That's one thing that's really tough, is remembering which version of each of these equations we're using. And if you solve that out in your calculator, I got 2.8 times 10 to the 10th joules, because this is potential energy. Energy is measured in joules. So going to be 2.8 times 10 to the 10th, which is quite large, but that's okay. It just means these charges were quite large there as well. Now, this was a simple case because there were only 2 charges. So Q1 and Q2 were really easy. I just got to point out that if you had a third charge in here, you would have to do this calculation a couple of times because you would have to account for Q1 and Q2 together and then you'd have to account for Q1 and Q3 and Q2 and Q3. So this gets magnifyingly more terrible the more charges you add. So typically we're going to stick with 2 charge examples, but I just want to point out that you could do this for more. It just gets worse in terms of the way you would have to how many calculations you'd have to make. That brings up the last important point to make about electrical potential energy, which is that electrical potential energy is a scalar. So what's a scalar? Well, it's the opposite of a vector. Vectors have magnitude and direction. Potential energy, though, energy does not have a direction to it. Energy is a scalar. It is just a magnitude. What that means is if you were to do that example with all 3 of those charges and you did the interaction between 1 and 2, and then 2 and 3, and then 1 and 3, you could just add up those answers, and that would give you the total potential energy. That is different, recall from electrical fields where it was a vector, and we had to take into account the direction of those vectors when adding things up. Okay, so that's electrical potential energy. That's half of what we're going to take a look at here today. But I do want to do one last example where we use that other equation where we have a field set up between 2 objects. So you're going to typically see this field thing in the context of parallel plates. Parallel plates are always kind of our big example for things here. So let's first kind of visualize the field. If you have a positive and a negative there, the electrical field would, of course, be between the 2 plates like this here. And then we're now considering an electron located midway between the 2 plates. And it just says how much work is required to move another electron from the positive plate to the negative plate. So it doesn't really matter that this electron's here. We're just saying, hey, if we had an electron here, how much work would be required to move it from the positive plate to the negative plate? This one is not one where it would be easy to use the electrical potential energy equation, KQ1, Q2 over R, because there are many charges on these plates. I don't know. I would have to add up so many different charges. So that's why we're going to use our other equation, which, just returning back to that slide so that we all can see it. That other equation, which is there, the U equals Q ED cosine theta. So copying that down here and then learning about how we use this one, delta UE Q E D cosine of theta. I just need to consider if I'm moving that electron, what do I plug in for all of these values here? Well, the first one that kind of trips us up is Q. Q, remember, is the charge of the object. And if I'm thinking about an electron, I have to remember that the elementary charge, that 1.6 times 10 to the minus 19th, is my Q for an electron. So my delta UE would be 1.6 times 10 to the minus 19th coulombs for an electron. Then E, the electric field, would be 3,500 newtons per coulomb. And then my distance would be the distance that I'm moving between the plates, 5 times 10 to the minus 3rd meters. And lastly, let's just check the angle thing. If I'm moving the electron from the top to the bottom, that's in the exact same direction as the field. So this would be the cosine of 0 degrees, which we know is 1. And so that's not going to matter there at all. You plug these in your calculator, and I get a very small number, 2.8, funny enough, kind of like that last example. But this one's times 10 to the minus 18th joules. So much smaller amount of work required to move it from the positive to the negative plate. Okay, so that's electrical potential energy. One thing that this example spurs is we were thinking about how much work is required to move an electron from the positive to the negative plate. But what if I wanted to think about that like abstractly? Like, how much work is it to take any charge from one to the other? Is there a way that I can like think about that? Well, funny enough, there actually is. Electrical potential is defined as the amount of work per charge required to move a charge through an electric field. So if you're thinking, hey, I want to know how much work it takes to move a charge, or how much work I get when I'm moving a charge through an electric field, this quantity will give it to you. Now, this quantity, that sounds really abstract, but it is actually the most useful electrical quantity in our world, because everybody has heard of electrical potential. You just know it as a different name. Electrical potential is the bad V word of voltage. I got to tell you, physicists don't use the word voltage much when they're talking about this variable. So you'll see electrical potential a lot, and in your head, you just have to translate, oh, yes, that means voltage. And so the unit of electrical potential is V, which stands, of course, for volts. So when I have a 12-volt battery, that means that it takes 12 volts of electrical potential to move the charge through that field. So that's giving me some information about how much work it takes to move charges through those fields there. So we can once again kind of define a quantity and then get some equations for it here. The first one just being that because it's the amount of work per charge, voltage is work divided by Q. But we had said earlier that work tells me how much potential energy I get, right? If I lift a ball, I do work on it, I give it potential energy. So work we can replace with potential energy. So we're going to kind of ignore that and say voltage is potential energy divided by Q. That leads me to my very first equation. The very first one that you're going to need to use, again, this first one's kind of more of just a definitional equation, is that remember that potential energy was K Q1 Q2 over R. If I divide it by Q, I can cross off one of the Q's and I'm left with this equation here that voltage is KQ over R. Now, if I wanted to find how much change in voltage there is between one place and another, it would just simply be the change in potential energy divided by Q. That's actually more useful often the other way, that the change in potential energy is Q times the change in voltage. So if I wanted to know how much energy I get from moving 10 electrons from one place to another, and I need the voltage, I could use that equation to give me that. And then this last one is also very useful as well. It's like that last equation for potential energy, that it's the change in potential is the electric field between maybe two plates times the distance, the gap that you are considering that potential between, and then, of course, the cosine of theta. This works the same way, the idea being that if you are in an electrical field, there's no difference in terms of potential between those two places because the distance there is not, it's perpendicular to the electrical field there. You'd only get an electrical potential difference between two places if there was actually a difference in the electric field that you're moving it down there. So it has to, again, satisfy that same angle requirement that we saw before. So I next want to take a look at an example, that same exact example we saw before. It says two conducting parallel plates that have that distance apart are producing a constant electric field of 3,500 newtons per coulomb between the plates. And it says, what's the electrical potential difference between the two plates? Now, again, you could define a electrical potential difference anywhere you wanted. So electrical potential is typically a, hey, I'm going to go from here to here. That's why if you were to test like a circuit in your house and you took like a tester out, you'd have to put one end in one place and one in another. There's no, oh, I'm going to take a tester and say, what's the electrical potential right here? You're going to typically be measuring a difference between two places. So here it's telling me I want the difference between the positive plate and the negative plate. So I know the difference between there. I know the distance between that place, and I know the electrical field between it. The electrical field is 3,500 newtons per coulomb. So I'm going to use that third equation, that the electrical potential difference is the electrical field strength times D times cosine of theta. That's just to check and make sure, again, you have to be going in the same direction, the distance, as the electrical field. If you went perpendicular, there would be a 90-degree angle. There would be no change in potential, which makes sense because you're just testing the same place. There'd be a constant electrical potential then, or no difference. So to get this one here, we're going to take the electrical field strength, 3,500 newtons per coulomb, times the distance, 5 times 10 to the minus third meters, and then times the cosine of my angle, which again is 0 degrees. Plug that in your calculator, and you actually get a nice number. This one ends up being 17.5 volts. Very, very typical voltage that you might have between two things. So even though with these kind of weird numbers, you actually do end up with voltages that are fairly real here. Okay, so that's taking a look at changes in voltage. But I want to next think about, like, could I define like a voltage field similar to the electrical field? And the answer is absolutely yes. Voltage, you can definitely define a field for it. We call them electrical potential lines. What an equal potential line. An equipotential line is a line or surface upon which the electrical potential is constant. Remember, we kind of just said on that very last example, in fact, that if you take a look at it, I were to go from the left side to the right side, I said the potential wouldn't change because you're going perpendicular to the electrical field there. Well, that applies anywhere you want around a charge. So this right here is the electrical potential diagram for two negative charges in there. And the idea being that these electrical charges, of course, will produce a electrical field diagram, and that if you were to be on this line, if you were to move from there to there, the change in voltage on that line would be zero because it's showing you where it is equal. In fact, the electrical potential there is 2. If I were to move from there to there, though, then I would be moving from -2 to -5. So that change in voltage would be 3 volts. I'm going from -2 to -5. And then if I were going from this one to this one, that's from -5 to -10. So my change in voltage would be 5 volts. So that's what electrical potential lines show me, is that they're where's a point where all the electrical potential is constant. If this is like going off like alarm bells for anybody, if you remember way back to earth science, this is exactly like doing a contour line plot for a surface. If you're thinking about like heights for like a mountain or something, these are like lines of constant height. Same thing is going to work here for potential. Now, because of the way that electrical fields and potentials interact, I want to show you this more complicated diagram, though I know it does look a little crazy, but once you get it, you're like, oh, this does make sense. I don't want to go backwards. So if you look at here, this is showing you now in blue, those are the electrical field lines for a negative charge. Remember, electrical field lines go from positive to negative, so they are going toward these negative charges. And I want you to notice, what is the angle between the electrical field line and these equipotential lines every single time? Well, if you look, those are all right angles. And that is not an accident. Remember that the change in voltage is ED cosine of theta. So if you have a 90-degree angle, if you move perpendicular to the electric field, the change in voltage is 0, aka an equipotential line. So there is no change in voltage. There'd be no work done in moving a charge along an equipotential line because it is perpendicular to the electric field. So that's the relationship between those two here. I added one last thing onto this slide here, just as a fun fact, which is typically going to be used with this equation down here, the equation that delta UE equals Q times delta V. If you wanted to find out the amount of work or energy that it takes to move a charge, let's say I'm moving a charge, let's say a 2 coulomb charge, and it starts right here and then it ends right there. Well, that amount of work, delta U, is the charge, so 2 coulombs times the change in voltage, and that change in voltage from there to there, it looks like is 8 volts. Now, we totally can like come up with like some units that would work really well, right? Coulombs and volts, I didn't define it, and let me do it for you here. Volts is equal to a joule divided by a coulomb. So if I did this one, 2 coulombs times 8 volts would give me 16 joules. So that unit works out really well. But what if I'm not talking about coulombs, but I'm like talking about an electron? Well, then I have to like do a lot of unit work to try to figure this out in coulombs, and that's not fun. So physicists have come up with another unit. That other unit is the electron volt. It's the amount of energy required to move one elementary charge through a potential difference of 1 volt. So that is what an electron volt is, and it's kind of hidden here at the bottom of my slide, so I'll write it that 1 electron volt is defined as 1.6 times 10 to the minus 19th joules if you do the math out. Okay, let's take a look at a practice problem and then be done for the day. Practice problem is 2 charges, +5 and +5, are separated by a distance 8 meters. Looks very familiar, but this time we're going to consider some different questions here. The first one is, what's the electric field strength halfway between the 2 charges? This is a flashback to the past where we talked about electric field strength. Remember, that is E, and E is KQ over R squared. So if I wanted to find the electric field strength halfway between the charges, so right at B, that means it's 4 meters from there to there, I would need to consider this equation. So I'm going to do it first for the first charge, Q1. So I'll plug in K, 8.99 times 10 to the ninth Newton meters squared per Coulomb squared times the charge, which is 5 coulombs, and divide by the distance, which is 4 meters, and then don't forget to square it. And I end up getting, when I do that, 2.8 times 10 to the ninth newtons per coulomb. So that we've seen before, doing electrical field strength. We've also seen that, hey, I made this easy. These are the same charges. So if I were to do charge 2 at this same point, that's also 4 meters away. So hopefully you believe me that it would be the same calculation, and you would also get 2.8 times 10 to the ninth newtons per coulomb. Then here is the key point. Remember that electric field is a vector, right? It points away from positive charges. So if I were to consider right at that point, this is the one from charge 1, and it would be pointing to the right. And this is the one from charge 2, and it would be pointing to the left. And they're the exact same amount. So what do you think the total electrical field strength is right in between them? The total is 0, because those two vectors will cancel out. I bring this up to point out that electrical field strength, E, is a vector. But electrical potential, just like electrical potential energy, is a scalar. It is not a vector. You don't have to consider direction at all. So if you wanted to find the electrical field or electric potential between the two charges, that would change your calculation. Voltage is KQ over R. So the voltage from the first one would be K, 8.99 times 10 to the ninth, Newton meters squared per Coulomb squared, times the charge, 5 coulombs, divided by the distance, 4 meters. Don't square it because there's no square in this one. And I get 1.1 times 10 to the 10th volts, which is very large. Hopefully you believe me that the second one would also be the same amount, because it would be the same calculation. And for this one, because they are scalars, I can just add these up. And so the total would be this one plus that one. And so my total voltage or total electrical potential would be 2.2 times 10 to the 10th voltage. So hopefully you can see and kind of compare and contrast electrical field with electrical potential. Scalars are so much easier. Okay, folks, I believe that is it for this video here. Thank you guys so much for watching. Have a fantastic rest of your day.